Non-metals take different nomenclature. The monoatomic anions are named by attaching the suffix IDE or "ide" to the first few letters root of the non-metal name. Let's take a look on the roots for common nonmetals. Let's have bromine, and the root is brom. For carbon, the root is carb. Chlor as the root for chlorine. Fluor is the root for fluorine. For hydrogen, the root is hyder. For iodine, the root is iod. For nitrogen, the root is nitar. Ox as the root for oxygen. Phosp for phosphorus. And sulf for sulfur. Let's take some examples. Bromine with a -1 charge. So if we add IDE or suffix I to the root of bromine, which is brom, it will become bromide. How about for sulfur? Sulfide. Nonmetals can also form polyatomic ions with oxygen. Then ion with less oxygen atoms ends with suffix ITE or ite, and the one with more oxygen atoms ends with suffix ATE or ate. Let's have an example. We have NO2 -1 and NO3 -1. For polyatomic ion NO2, we use suffix ITE added to the root name of the first nonmetal element. In this case, the first nonmetal element is nitrogen, and with the root name nitar. So therefore, the name of the polyatomic ion would be nitrite. How about the second polyatomic ion, which bears more oxygen? Definitely, we're going to use the suffix ATE or ate. So the name would be nitrate. The halogens can form 4 different polyatomic ions with oxygen. Each ion is named differently depending on the number of oxygen atoms present in it. Examples. How are we going to name a polyatomic ion formed between chlorine and oxygen with only one oxygen on it? How about if there are 2 oxygen atoms? That is ClO2 -1. What if it has 3 oxygen atoms? That would be ClO3 -1. And with 4 oxygen atoms, ClO4 -1. How are we going to name the first anion? We just simply put the prefix hypo. So, the name of the first anion would be hypochlorite. How about the second anion with 2 oxygen atoms? The name would be chlorite. How about the third ion or an ion? It will be chlorate. How about for the last polyatomic ion? We add prefix per. So the correct answer would be perchlorate. Let's try to name the four anions of iodine. Let's have iodine with one atom of oxygen, that is IO, -1. Iodine with two atoms of oxygen, that is IO2, -1. Iodine with three atoms of oxygen, that is IO3, -1. And iodine with four atoms of oxygen, that is IO4, -1. How are we going to name the first anion of iodine? We just simply put prefix hypo in a word iodide. So the correct name would be hypoiodide. How about the second anion of iodine? It's iodide. How about the third anion of iodine? It is iodate. How about the last or the fourth anion of iodine? Periodate. Here, you are going to remember a few things. For the first two anions of iodine, you can see the suffixes ite with their names. For the last two anions of iodine, we are using suffixes ate on their names. And for the first anion of iodine with the least number of oxygen atoms, we use prefix hypo. And for the anion of iodine with the most number of oxygen, we use the prefix per. In some cases, the oxygen in the polyatomic ions is substituted with a sulfur atom. In this case, a prefix thio is added to the name of the anion. Example, OCN-1 or cyanate, when O is substituted by S, it will become SCN-1 or named as thiocyanate. Ternary polyatomic ions or radicals consisting of three different elements may be formed by the addition of hydrogen atoms to binary polyatomic ions. If there is only one type of ternary ion formed, a prefix bi is added to indicate types of ions formed with hydrogen. Greek prefixes are used to indicate the number of hydrogen atoms present in an ion. Let's take a look on some examples. CO3-2 or carbonate, when H is added to it, it will form a ternary ion, HCO3-1. And since there is only one type of ternary ion formed here, so we are going to use the prefix bi in naming. So you just simply add bi, the prefix bi, in the word carbonate. So the correct name would be, of this ion would be bicarbonate. Let's have the second example. PO4-3 or phosphate. With the addition of hydrogen, there are two ternary ion formed, which are HPO4-2 and H2PO4-1. This time, we're going to use Greek prefixes to indicate the number of hydrogen atoms. So for the first ternary ion formed, the correct name would be hydrogen phosphate. For the second ion, since there are two hydrogen atoms, so we use the prefix di. So the name would be dihydrogen phosphate. This time, let's talk about molecules. When atoms of nonmetals share electrons, they form an electrically neutral aggregate called molecule. Non-metallic elements exist in nature as diatomic molecules, consisting of two atoms of the same element. They are more stable this way rather than as individual atoms. Diatomic molecules are nitrogen, oxygen, hydrogen, fluorine, chlorine, bromine, and iodine. Among these examples, bromine is liquid, iodine is solid, and the rest are gases at room temperature. Molecules can also be composed of atoms of different elements, whether diatomic or polyatomic. Let's have examples under diatomic molecules. Under diatomic molecule, we have HCl, or hydrogen chloride. Hydrogen chloride is a colorless gas which forms white fumes of hydrochloric acid upon contact with atmospheric water vapor. Hydrogen chloride gas and hydrochloric acid are important in technology and industry. We also have HBr, or hydrogen bromide. Hydrogen bromide is a heteronuclear diatomic molecular compound. Hydrogen bromide is very soluble in water, forming hydrobromic acid. We also have H2S, or dihydrogen sulfide. Dihydrogen sulfide is a gas commonly found during the drilling and production of crude oil and natural gas. Of course, under diatomic molecules, we have H2O, commonly known as water. Water is dubbed as the universal solvent. We also have CO2, or carbon dioxide. Carbon dioxide occurs naturally in Earth's atmosphere as a trace gas. And we have also N2O, which is called as nitrous oxide. Nitrous oxide is a colorless, sweet-tasting gas. It is also known as the laughing gas. We also have polyatomic ion molecules. Under this, we have C6H12O6, or a simple sugar called glucose. We also have CH, H10N4O2. This is the world's most widely consumed psychoactive drug, the one that is in our coffee.